When a car stops, a spring relaxes, or a hot cup of coffee cools down, where does the energy go? The goal of this presentation is to understand one of the important ideas in physics and mechanics, the Newton's law. To understand that clearly, we first need to build the language of mechanics: force, motion, and work. Once we understand how a force acting through a distance transfers energy, the Newton's law and also the first law of thermodynamics become much more intuitive. Assume we have an object moving at 20 meters per second. Can you tell me where it will be 5 seconds from now? For that, we need to know whether its motion is changing. Kinematics describe what we see, its position, velocity, and acceleration. But if the object accelerates, brakes, or turns, we need to ask why. That's dynamics, the study of forces that change motion. So a simple way to remember is kinematics describes the motion, dynamics explain the cause of motion. Assume I push a wall as shown in this figure by this small area. Every small piece on this surface get the push, and how concentrated this push is called pressure. Its unit is Pascal. That means 1 Newton per meter square. The pressure is then force perpendicular to a surface divided by the surface area in Newton per meter square. Note that pressure is not itself a force. Pressure acting on an area produces a force. Just give you an understanding of pressure. Assume that we are standing near sea level, and the air around us exerts the pressure about 100,000 Pascal, and it's equal around 100 kilopascal. Assume I tell you that I'm applying a force of 100 newtons to this box. Do you know what will happen? But which way will it move? That's the important point. 100 newton tells us how strong the force is, but it does not tell us where the force is pointing. So 100 newton alone is incomplete. Look here. Every one of these forces has exactly the same magnitude as shown by the length of this arrow. But they are not the same force. This pushed the box towards its right, this pushed the box towards its left, this pushed the box upward, and so on and so forth. Therefore, this is important to know that a force is a vector which needs both magnitude and direction. Now let's talk about first Newton's law. For a while, hockey puck sliding on nearly frictionless ice. If we give it the puck one push and then stop touching, if friction is zero, it would keep moving in a straight line at the same speed. A force is only needed when you want to change the velocity. This is the heart of Newton's first law. In this case, since there is no net forcing acting on moving puck, no change in velocity. In short, Newton's first law states that an object will maintain a constant velocity if and only if the net external force acting on it is exactly zero. In the first law, we have seen that when the net force is zero, velocity is constant. Now, if the net force is not zero, what does happen? Assume I have a ball in my hand at a given height h. In this case, the net force is zero because the weight of ball is balanced with the upward force applied by my hand. If now I release this ball, the balance is disappeared, and therefore the net force is not zero. The ball gets downward acceleration, and the net force is balanced by mass of ball multiplied by its downward acceleration, which is gravitational acceleration. Another example, let's consider mass in a spring system. If the net force is zero, our mass is in its equilibrium as shown here. If I stretch the mass, the net force is no longer zero, and this net force, according to Hooke's law, is balanced with mass of object. Now that we understand force and acceleration, we are ready to move to energy. We'll begin with work, how forces transfer energy, and then introduce three forms of mechanical energy: kinetic energy, gravitational potential, and elastic potential energy. A force does work when it acts through a distance. For a constant force, the work is simply the area under the rectangle under the force distance curve as shown here. Work is equal force multiplied by this distance. But what if the force changes and is not constant? Then we divide the motion into many tiny distances. Each small rectangle represents a tiny amount of work, and adding them all give us this formula. The total work is integral between 0 and the force dx. So, in general, work is the area under the force distance curve. Now we are ready to introduce energy. Work is a way of transferring energy. When work is done on an object, its energy changes. Therefore, work transfer energy. What is energy? Energy is an ability to do work, and its unit is joule. But where can the energy be stored, and what happens to it afterward? Looking at this figure, the arcer uses chemical energy from the body to do work on the bow. The energy is stored in the bent bow as elastic potential energy. When the string is released, the stored energy is transferred mainly into the motion of the arrow. Energy associated with motion is called kinetic energy. Kinetic and gravitational potential energy are defined as follows. Kinetic energy depends on the square of an object's velocity, while gravitational potential energy depends on its height relative to a chosen reference level. That's why I put here delta H. In other words, kinetic energy is associated with motion, while potential energy is associated with position. Let's start by Hooke's law in order to explain elastic energy deformation in a spring. Hooke's law is given by this formula, which indicates a restoring force. It means if we stretch the spring to the right, the spring pulls back to the left. But here, to stretch or compress a spring, we, as an external agent, must apply a force that exactly opposes the spring's restoring force Fs. That's why we have external force F given by Kx, because F is equal minus Fs. The work we do in this case is the area under F force X curve, which after a simple mathematical manipulations, we get to this elastic potential energy. I discussed briefly here about different energy units. Energy is measured in joules, but 1 joule is very small. So just as we use kilometers instead of millions of millimeters, we use kilojoules, megajoules, gigajoules, and eventually, for example, exajoules and zetajoules for increasingly large energy systems. To make these huge numbers more intuitive, we can also use a simple human unit which is about 10 megajoule. Roughly a dietary energy one person using in a day. I have provided a list of comparison to give you more insights on these energy units. In electricity, we often use the kilowatt hour. 1 kilowatt hour is equal 3.6 megajoule, or 3,600 kilojoule. And in heating and cooling, specifically in United States, we often encounter the BTU. 1 BTU is about 1.06 kilojoule. Roughly the energy needed to warm 1 pound of water by 1 degree of Fahrenheit. For much larger energy quantities, we use the ton of oil equivalent, or TOE. 1 ton TOE is approximately 41.9 gigajoule, representing approximately the energy contained in 1 ton of crude oil.